Welcome back to this next video in which we are discussing polynomial rings that are unique factorization domains. Okay, so what we now need to show is that if we have this primitive polynomial here, p prime of x, that firstly it can be factored into a product of irreducibles in our polynomial ring R adjoin x, and secondly, that this factorization into irreducibles is unique up to the fact that you can change the associates that you're using for the irreducibles. Okay, so how are we going to now do this? Well, what we're going to do is we're going to move over to now working in the ring of polynomials that is over the fraction field of the unique factorization domain R. Okay, so because R is a unique factorization domain and a unique factorization domain is an integral domain, it is possible to generate the fraction field, capital F here, so we'll denote the fraction field of our unique factorization domain by capital F here. Okay, and remember that this fraction field will consist of all of the fractions, which is a numerator over a denominator, where the numerator is from our initial integral domain R and the denominator is also from our initial integral domain R, but the denominator is not allowed to be the zero element. And then of course what you have to do is you have to divide that set of all fractions into equivalence classes of equivalent fractions, and then those equivalence classes of equivalent fractions then become the elements of your fraction field, and you define an addition and a multiplication law on those equivalence classes. So that's just a reminder of the fraction field. We do have an entire video on fraction fields in this video, in this playlist on ring theory. Okay, so if you're a bit rusty on fraction fields, I advise that you go and watch that. Okay, so remember the integral domain will be entirely contained within the fraction field. There is a very natural injective homomorphism from the integral domain into its fraction field. Okay, so what does this mean then? Well, this means that our primitive polynomial p prime of x, which at the moment is an element of our ring of polynomials over the unique factorization domain R, this can also be thought of as being an element of the ring of polynomials over our fraction field. Okay, and the reason this is true is because R is properly contained within the fraction field, so all of these coefficients that are in front of the powers of x in any polynomial in the ring of polynomials R adjoin x, those are all going to be in the field capital F here. Okay, so all polynomials that are in this ring of polynomials are going to be in this ring of polynomials as well. So p prime of x will be in the ring of polynomials over our fraction field capital F here. Okay, now, why is that an interesting thing to do? Why should we move suddenly to working in the ring of polynomials of the fraction field rather than the initial unique factorization domain? Well, the reason is that rings of polynomials that are over a field, which of course the fraction field is, are Euclidean domains, and all Euclidean domains are principal ideal domains, and all principal ideal domains are unique factorization domains. Okay, so I can instantly conclude that this ring of polynomials over the fraction field is a unique factorization domain, and of course that means that I can now factorize p prime of x down into a string of irreducibles. Okay, and we have a hope that we might be able to use that to find a string of irreducibles that we can multiply together in the ring of polynomials over our unique factorization domain to get p prime of x. Okay, so let's firstly do it in the ring of polynomials over the fraction field. Okay, so I'm going to write this in a different way to the way I usually do. Okay, so up here when I described being able to write any element as a product of those of irreducibles, I said that you could write it in this form with a unit out the front and then powers of your irreducibles here. Okay, that's, if you like, the tidy way of writing a factorization into irreducibles. The way I'm now going to write it is the more messy way, okay, where you just have irreducible following irreducible following irreducible. In a way, it's less tidy, but in the context of this proof, it's actually easier to work with than this, okay? Far easier to work with than this. So instead of writing it like this, I'm going to instead write it as p prime of x here, our primitive polynomial, which is now an element of the ring of polynomials over the fraction field, can be written as the product of loads of irreducible polynomials. Okay, and I hope the notation isn't going to get confusing here. So I'm going to initially denote these irreducible polynomials like so. Capital P1 of x, capital P2 of x, and it will just go on all the way up to capital Pn of x. And you might ask, well, what if you have higher powers of them? Okay, I'm writing it in a messy way, so some of these might be repeated polynomials. Okay, so rather than grouping them all together and having it raised to one power, I've got them all separately. And you might also ask, where's the unit gone? Well, I've just swallowed the unit into one of the polynomials. Okay, so this is exactly equivalent to what we would normally write for our factorization into irreducibles. It's just the more blunt form of it. And for the context of this proof, it's going to be easier to work with blunt factorizations into irreducibles rather than the more tidy factorizations into irreducibles. Okay, so here I have now written my polynomial p prime of x as the product of loads of irreducible polynomials. Okay, and they're all irreducible in the fraction field adjoin x here, this ring of polynomials over the fraction field. So pi, capital Pi of x, these are all polynomials in the fraction field, capital F adjoin x here. Okay, like so. Right, and remember they are all irreducible, so I'll just make a note of that. They're irreducible in here. Okay, so these are irreducible. Okay, right. So what I now want to do then is use this to find a product of polynomials that are actually in the ring of polynomials over the unique factorization domain, which are irreducible. Okay, these we don't even know that they're in the ring of polynomials over the unique factorization domain, and certainly we don't at the moment know that they're irreducible in there. Okay, so firstly we need to find some polynomials that are in here, and then we need to hope and pray that they do actually turn out to be irreducible in here. Okay, so firstly, let's actually just try and find some polynomials. Let's just play around with this. We don't know that this is going to work. Well, I do. Okay, but initially, let's just try and find a string of polynomials that we can multiply together, which are going to give p prime of x and which are in the ring of polynomials over the unique factorization domain. And we're somehow going to construct them from these ones. Okay, so how are we going to go from these polynomials which are in the ring of polynomials over the fraction field to polynomials which are in the ring of polynomials over the unique factorization domain? Well, this is where it would be very helpful for you to have watched the video on Gauss's lemma. Okay, and indeed, really, to follow this proof, you do need to have watched the previous video in this playlist entitled Gauss's lemma. We're going to later use the corollary of Gauss's lemma that I state at the end of that video. Okay. But we're now going to use the actual Gauss's lemma itself. We're going to use the proof technique that we use in the proof of Gauss's lemma, the exact same proof technique as we employed there. So it would really be helpful if you'd watch that video before watching this video. Okay, so I will sort of go over the proof technique again, but I won't do it maybe as slowly as I did there. Okay, so the idea is then that we need to turn these polynomials, which are currently in the ring of polynomials where the coefficients are from the fraction field of the unique factorization domain R, into polynomials that are actually in the ring of polynomials over the unique factorization domain R. Okay, so we need to get rid of the fractions, basically. And how do we do this? Well, we need to somehow get rid of the denominators. Okay, so let me write one of these out explicitly. P1 of x. Let me write P1 of x out explicitly. Okay, and I'll do the coefficients rather than trying to get some apt nomenclature for the coefficients, since the polynomial is called P1 of x. I'll just call the coefficients completely different things. Okay, so the names of the coefficients won't relate to the name of the polynomial here. Okay, I don't know. The nomenclature would just get too complicated if I tried to actually name them after the polynomial. So I'll just have, it'll be a0 over a0 prime here, plus a1 over a1 prime, and I hope you sort of understand what I'm doing here, plus all the way up to, and I'll just make sure this is in view firstly, an over an prime x to the n here. So here's my picture, my written out explicitly version of P1 of x here. Okay, so this is this. Right, now all of these things, a0, a1, all the way up to an, and all of the primes as well, so all the ai's and all of the ai primes, these are all just elements of the unique factorization domain. So these things, these coefficients in the polynomial, so I'll just circle them in pink here, these are just fractions, they're just elements of the fraction field, capital F. Now of course really the elements of the fraction field, capital F, are not fractions, they're whole equivalence classes of fractions, okay, but these are just representatives from those equivalence classes. Okay, so here is my polynomial. This is what I'm supposing is my polynomial p1 of x, and as I say, I have not attempted to make the coefficients' names relevant to the name of the polynomial. Okay, so how then can we turn this? How can we take this and turn it into something that is in the ring of polynomials over the unique factorization domain and seems to be very relevant to this polynomial? Okay, so is very much so related to this polynomial. Well, the idea is that what we can do is we can multiply through by the product of all the denominators here. Okay, so if I construct the thing a0 prime times a1 prime all the way along to times an prime, okay, like so, okay, which is a non-zero element in the unique factorization domain capital R. So this is going to be some element of our unique factorization domain capital R, and I can also conclude that it is not equal to 0. Okay, and the reason I can conclude that is that, remember, this is an integral domain. All of these denominators are non-zero because, remember, we insist that the denominator of a fraction cannot be 0. So we're multiplying those of non-zero elements together, and therefore we're going to end up with something that's non-zero. So this is some non-zero element of the unique factorization domain. I can certainly multiply this with my polynomial p1 of x, okay, and of course you'll distribute this out in the normal way, okay, and it will cancel the denominators. So when it multiplies this coefficient here, a0 prime will cancel. When it multiplies this coefficient here, the a1 prime will cancel, okay, etc. Or really, more strictly, what will happen is you'll multiply this polynomial, this fraction, which strictly speaking would be the fraction over 1 here, if we were thinking of it as an element of the fraction field, capital F. You'll multiply it with a representative from this equivalence class of fraction. You might as well take this representative here, okay, and then you'll find another fraction that's in the same equivalence class as it, which will have the cancelled out, in this case, a1 prime with the a1 prime in the denominator. Okay, and then you'll reduce it back to something of the form, some element of the unique factorization domain over 1. Okay, that's me spelling out exactly in full rigour what you're doing in the fraction field, capital F. Of course, we have intuition for how fractions work, so hopefully you can appreciate that when I multiply through by this thing, the denominators are all going to cancel, and I'm going to end up with coefficients that are back in my unique factorization domain, capital R. Okay, you should probably take a little bit of time out to think exactly in full rigour what you're doing in terms of the fraction field. Okay, but we have good intuition for how fractions work, so I don't think that a further explanation of that's needed. Okay, now what does require further explanation is the fact that we're going to do this for all these polynomials, not just p1 of x, we're going to do it for p2 of x all the way up to pn of x. Okay, we will multiply all of the denominators in the coefficients of p2 of x together, and so on for all of these, and we'll add those to this great big product. So I will construct something which I'll call D, which will be a great big product of all of the denominators of all n of these polynomials. So it will have all of these ones in firstly, so it will have a0 prime, a1 prime, all the way up to an prime, but then it won't stop there, it will go on. Okay, so we'll do it the same thing for p2 of x here, and all the way up to pn of x, and get a massive great big product here. Okay, and then of course what I can do is multiply both sides of this equation by this d. Okay, and what would I end up with then? I will end up with an equation like this. D times p prime of x here, okay, the polynomial of interest, p prime of x, okay, is equal to, and here are my new modified polynomials, and I'll call these lowercase p1 of x, okay, so once I've taken capital P1 of x and got rid of all its denominators, I'm now calling it lowercase p1 of x. Similarly for capital P2 of x, it's now lowercase p2 of x, and then we'll go all the way up to lowercase pn of x here. Okay, and now the big thing that's changed now is that all of these polynomials, I don't have to think of them as being in the ring of polynomials over the fraction field now. I can get rid of the fraction field, okay, and in fact we're not going to use the fraction field anymore. Okay, well, we will have to go back to the fraction field when we want to check uniqueness, but for just proof of existence of a factorization into irreducibles, we don't need the fraction field anymore. Okay, and these now are all elements of the ring of polynomials over the unique factorization domain, R adjoin X here. Okay, so this is looking hopeful. I've got some very much so related polynomials, my little p1 of x, little p2 of x, all the way up to little pn of x, that are in the ring of polynomials over the unique factorization domain, and which are multiplying together to give R. Not quite p prime of x, but d times p prime of x. Okay, so there's still a little bit of work that needs to be done here. Okay, because what I want is p prime of x written as a product of polynomials that are in my ring of polynomials over the unique factorization domain. Okay, so I somehow need to get rid of this d here. Okay, now of course it's absolutely easy if it's a unit. If d is a unit, then just multiply both sides by its multiplicative inverse. Okay, just multiply one of these polynomials by its multiplicative inverse, and then you've got a string of polynomials that are all in the ring of polynomials over the unique factorization domain that is making p prime of x. What's more difficult if it's not a unit. So let's now take on that case, and this is where we are going to use the same ingenious argument as we used in Gauss's lemma, the key to proving Gauss's lemma, and it's going to be the key here. Okay, so here it comes. Okay, so if d is not a unit, then it can be factored into a bunch of irreducibles in the unique factorization domain R, because after all d is just an element of R. Okay, so because R is a unique factorization domain, it can be factored into a string of irreducibles in a unique way. Okay, so this is where the notation is going to get really confusing because I'm too lazy to come up with some new notation. Okay, I'm going to denote the irreducibles that I can factor it into as P1, P2 all the way up to Pn, and note again I am using the blunt way of writing a factorization into irreducibles. Again, it just makes it easier. This argument becomes easier if you just use the blunt way rather than the neat, pretty way. Okay, so here we go. D is factored into a bunch of irreducibles, and note these are not the same as the polynomials p1 of x, p2 of x. These are now elements of my unique factorization domain, so the pi's are all elements of R. Okay, so now let's actually write out the equation that I have in full. So what I've now got is that p1 times p2 all the way up to times pn, where these are all now viewed as constant polynomials, times the non-constant primitive polynomial p prime of x is equal to these polynomials p1 of x all the way along to pn of x, okay, which are these modified polynomials that I got from those polynomials that were irreducible in my ring of polynomials over the fraction field. Okay, right, so let's try now to get rid of the p1, the p2, all the way up to the pn here. So how am I going to do this? Well, what I need to prove is that these are in these polynomials over here. Okay, if I want to get rid of this p1 here, what do I have to do? Well, it must be the case that I can cancel it in some way. Okay, remember the ring, this equation is in the ring of polynomials over the unique factorization domain. Okay, a unique factorization domain is an integral domain, so the ring of polynomials over the unique factorization domain is an integral domain. Okay, so if it was the case that this was factorizable out of one of these polynomials on the right here, okay, so if it was the case, for instance, that I could completely pull out p1 from p1 of x here, okay, if it was the case that all of the coefficients in p1 of x were multiples of p1, okay, and they had it in their unique factorization domains, i.e. it was a common divisor, I could pull it out, and then because it's an integral domain I could just cancel it off. That's what I want to do. Okay, so I now need to prove that it's always the case that you can cancel these. It's always the case that in these polynomials over here... Oh, and by the way, I didn't mean to suggest that this n was the same as this n. Let's change that. Let's make this n bar. Okay, of course it is not necessary that the number of irreducibles that D is factorizable into is going to be the same as the number of polynomials that I had there. Okay, of course that's not true. Okay, it doesn't need to be true at all. So I'll turn that into m bar. It was just because I was too lazy to come up with a new symbol. Okay, right, so where was I? So I want to prove that I can always cancel these away, basically. Okay, and this is the ingenious part. So I'm going to use a ring homomorphism from the ring of polynomials over the unique factorization domain into a ring of polynomials over the unique factorization domain quotiented out by some ideal. Okay, and what I'm going to use as my ideal is the principal ideal generated by one of these. So let me firstly just take one of them. Okay, so I'm going to do this one by one. So we'll start off with P1 here, and I want to get rid of P1. I want to cancel it from both sides. So to do that, I need to prove that one of these polynomials on the right-hand side has P1 as a common divisor of all of its coefficients, that I can pull it out and then cancel. Okay, so what I'm going to now consider is the principal ideal generated by P1, which of course is going to be a prime ideal in the unique factorization domain capital R. Okay, a non-zero prime ideal in fact. Okay, why, you might ask? Well, it's because in a unique factorization domain we know that the definitions of irreducible element and prime element completely overlap. All irreducibles are prime. We know that P1 is irreducible, so it's also prime. The definition of a prime is that when you generate its principal ideal, you end up with a non-zero prime ideal. Okay, so this is a non-zero prime ideal. What we can now do is quotient R out by the principal ideal generated by P1, and what we'll get is an integral domain. Okay, and what we're now going to consider is the ring homomorphism, where we map all of the polynomials in the ring of polynomials over the unique factorization domain R onto what they are modulo this ideal, i.e. we're going to map them onto R quotiented out by the principal ideal generated by P1 adjoin X. Okay? Now, why is this going to be so nice? Okay, well, I'll state an incredible property of this first of all, and then we'll see why this is going to work so incredibly. Okay, the first thing to note is that because the principal ideal generated by P1 is a prime ideal, okay, a non-zero prime ideal, and remember all prime ideals are proper ideals, then when we quotient R out by this prime ideal, it's a theorem that we proved many videos ago. I don't remember which video exactly in the playlist on ring theory, but we did prove it in some video, that whenever you, probably the video entitled Prime Ideals, whenever you quotient out a non-zero commutative ring, which this certainly is, by a prime ideal, you always end up with an integral domain. Okay, so R quotiented out by the principal ideal generated by P1 is an integral domain, and therefore the ring of polynomials over that is also going to be an integral domain. So we can now extend that to the entire thing. The entire thing is going to be an integral domain here. Okay, now that's good. Okay, that's going to be very good. We're about to use the fact that this is ring of polynomials here as an integral domain. So now let's take this equation that I've got here, which is an equation that I had in the ring of polynomials over my unique factorization domain, and let's take it into here. Okay, let's make it an equation in here. Now how can I do that? I can apply my mapping here to both sides of the equation. So let's now do this. Now when I apply phi to this side of the equation here, remember what phi does. It takes all polynomials and it goes to all of the coefficients in front of the powers of x and says, are you in the ideal here? Okay, and if you are in the ideal, well, it takes all of the coefficients to what they are modulo the ideal. Okay, so it takes all of the coefficients that are in the unique factorization domain R here and says, well, what would they be mapped onto in the quotient ring here, R quotiented out by the principal ideal generated by P1. Now, in this case, look, we've got a P1 out the front here. You could bring this into P prime of x, and that means that all your coefficients here are going to be multiples of P1 of x, of P1. Okay, so all the coefficients of this polynomial on the left hand side here are going to be multiples of P1 because there's that P1 that we've got right out the front here. Okay, now what does that mean? That all of them are going to be in the principal ideal generated by P1. So this left-hand side polynomial here, it's just a polynomial where all of the coefficients are actually in the principal ideal generated by P1. And when we take that polynomial, map it onto what it is modulo that principal ideal generated by P1, it's just going to go into the 0 polynomial. So the left-hand side here is going to be the 0 polynomial. That polynomial modulo the principal ideal generated by P1 is very boring. Now, what happens to the right-hand side? Well, we can say much less about the right-hand side. What we can say is that we've got phi of this great big product, and because phi is a ring homomorphism, we can split this into phi of P1 of x times phi of P2 of x times all the way up to phi of Pn of x, like so. Okay, where you're now multiplying these polynomials, take a modulo this principal ideal generated by P1, okay, and multiplying them together in this ring of polynomials over this quotient ring rather than the original ring of polynomials over the unique factorization domain. Okay, now, because this is an integral domain, we know that the only way that you can multiply these polynomials together and get 0 is if one of them is 0. Okay, at least one of them must be 0. So one of these must be 0. Okay, let's say, for sake of argument, that it's phi of P1 of x here. Okay, so phi of P1 of x, let's say, is taken onto the 0 polynomial. But what does it mean to be taken onto the 0 polynomial about P1 of x? It means that all of the coefficients of P1 of x must have been in the principal ideal generated by P1. Otherwise, they wouldn't have all been taken onto 0 in the quotient ring, and therefore the polynomial wouldn't have been taken onto the 0 polynomial, okay, when we took it modulo that ideal. So what that now means then is that P1 of x, all of the coefficients are multiples of P1, and therefore P1 was a common divisor of all of the coefficients of P1 of x. So indeed, I could have pulled out a P1 from my P1 of x, and then of course I could have cancelled them off on both sides. Now, I just took P1 of x arbitrarily. It might not have been P1 of x, it might have been one of the others. The point is that one of them will have had P1 as a divisor of all of its coefficients, as a common divisor of all of its coefficients. Okay, and therefore it would have been possible to pull that out and then cancel it away. So what does this now mean then? This now means that I can take, I can do this for each one of these. Okay, I can get rid of all of these P1, P2, all the way up to Pn. Okay, all of them will at some point be a common divisor of one of these polynomials on the right hand side here. So you can indeed cancel them away. Okay, so you'll get now that P prime of x is equal to, and the final thing that I'll write here, I'll call it P1 bar of x times P2 bar of x all the way up to Pn bar of x. Okay, so I hope you understand what I've been saying here. Okay, we are going to go through this process of cancelling away all of these P1, P2, all the way up to Pn. Okay, we're going to go through this process for all of them, and the argument applies just as well for all of them. You just have to change the ideal that you're working with here, change the ideal which you're going to take the polynomials modulo to, okay, from the principal ideal generated by P1 to the principal ideal generated by P2 or P3 all the way up to Pn, etc., Pn bar rather, and you can cancel them off, okay, and there'll be different polynomials potentially each time, and you just need to gradually cancel it off. So these polynomials that you'll have in the final expression are going to be slightly different from the polynomials that you had in the initial expression. Okay, so you'll end up then with something that looks like this. P prime of x is equal to P1 bar of x times P2 bar of x all the way up to Pn bar of x, like so. Okay, and note, all of these polynomials that you've got here, the Pi bar of x, they are still in the ring of polynomials over the unique factorization domain R. So we haven't changed that. All we've done is pull some common divisors out of their coefficients, okay, to get rid of that irreducible factorization of d on the other side. Okay, so what I have successfully now done then is written my polynomial P prime of x as a product of these polynomials that are in my unique factorization domain R adjoin x. Okay, so the question now is, are these polynomials that I'm left with here, P1 bar of x, P2 bar of x, all the way up to Pn bar of x, Are they irreducible? Okay, fantastic. I have a product that is giving p prime of x, and they are polynomials from my polynomial ring over the unique factorization domain, but are they actually irreducible? Okay, well, what we now need to understand is that they will indeed be irreducible. But I think we'll have a break here, and then we'll take that question on in the next video.